I'm going to try and talk today a bit about Graphcore. I don't know who's heard of Graphcore before they saw the kind of abstract here, just trying to get an idea. Okay. I'm going to talk about us, and I'm going to talk about IPUs, the chip we make. The other thing I'm going to talk about is go to the other end of the spectrum, away from hardware to software, and talk about TensorFlow. I expect the hands are going to be bigger. Who here codes in TensorFlow regularly? Oh, that's more than I imagined, actually. So that's like, of those people who kind of pays attention to the underlying platform, who kind of thinks about kind of the GPU or CPU that's kind of running underneath and really cares about that in different ways. Actually, we find that we have like people with different use cases. Some people want to say, I just want to define this model, I don't care about hardware underneath, I just want it to work. And some people are real, kind of really want flops, really need to kind of, because the training takes so long, and really want to know about everything going on underneath. What I'm going to really want to talk about today, and try and kind of fit this into the time, is the everything in between. I think what might be interesting to the audience here is what goes on behind TensorFlow when you kind of like create that computation graph and say, right now go and run, kind of what's happening underneath to kind of get it running on some hardware. And I'm going to talk about it with respect to our hardware, which is new. So, let's get going. Graphcore. So, Graphcore, we're a new company. We've been around for about 3.5 years now. We actually found another company, so we've been going for a bit longer than that. And we're up to about 350 people worldwide. It takes quite a lot of people to create a new hardware and software platform for machine learning. We are mainly based at Bristol in the southwest. That's where our head office is and where most of our core engineering are. But now we're kind of expanding that engineering effort into Cambridge in the UK. Through acquisition, we've also got a reasonably large engineering department in Oslo in Norway as well, looking at Graphcore, which I'm not going to talk too much about today. And then we have people in the US and China who are more kind of customer focused, both in engineering and sales. So that's kind of where we are now. We're getting to a reasonable size. What are we kind of doing with all those people? What do we try to do? Well, this is the official kind of company mission. So we're creating a new chip, and what we want that chip to be is the platform that lets us move forward with machine intelligence, machine learning if you like, but kind of anything to do with kind of intelligent compute, about reasoning in an intelligent way. And that's the kind of mission that you kind of set out kind of 4 or 5 years ago to create a chip to do that, that kind of enables that a lot better than existing platforms do now. And existing platforms I'm talking about kind of CPUs and GPUs. So kind of when we wanted to do that, kind of we had to look at a few different things. We wanted to look at kind of where's the market going, what's kind of happening in this area, and also kind of what's the case with the hardware, kind of what's happening with chip development nowadays, kind of what kind of constraints are we under to produce a computing platform. So I'm going to kind of briefly touch on those. I could talk a lot about kind of the philosophy behind the chip and design. I'm not going to do too much of that today, so we want to get into software. But let's talk about machine learning. So one thing that's like really, really clear is that the amount of compute that's required for machine learning has been growing and growing and growing. There's a real hunger for compute. And you can see that historically. This isn't our chart, I don't believe, it's actually AI. You can see how, as time goes on, the number of kind of petaflops, this is a logarithmic scale as well, right, has been going up exponentially. So the amount of compute we need to do stuff is going up. It's kind of related to the fact, actually related to that, interestingly, is the amount of data required to train kind of new insights in machine learning is also going up. The two go hand in hand, and they're strongly correlated. There's some other kind of good works in that. For example, Baidu did some really good studies on that as well. So, first thing, need a lot more compute. Need a lot of multipliers, basically. What else is there? Well, the other thing that actually is becoming more interestingly more recently, and I'm going to touch on this a bit towards the end as well, is that model size is also going up. So the number of parameters, the amount of like storage you need to encode something that's being learned is going up. Again, we have, this is not logarithmic scale, but again we have kind of, there are fewer points on this, but you can see from ResNet 50 and kind of, actually around here it'd be quite interesting. If you look at business models, there'd be a bit of like churn around here because it went up and down a bit, kind of from the BGGs to AlexNets to ResNets and things like that. But kind of definitely as we go up, we can see that as we kind of get into trying to encode more information than just that vision classification into kind of language understanding, things are getting larger. Blur, which has been really a kind of like a fundamental model in the last couple of years in terms of language understanding, is 330 million parameters as opposed to the 25 in kind of ResNet, which kind of made such a big splash in image classification. And then more recently, OpenAI's GPT-2 is kind of then an order bigger than that, and this is not going to stop for a while as well. So the requirements on, I guess the general thing is the requirements on compute are getting bigger. The other thing that was kind of very clear to us at that point is that the type of compute that gets done is going to have to be a bit different in that these kind of trends we have to accommodate for them and kind of like provide very high performance compute platforms. But actually, we can't just keep on going, throwing more storage, throwing more flops at a problem. That algorithmically we're going to have to also increase our efficiency as well. So actually kind of get more bang for your buck, like more kind of learning insights for the amount of storage and the amount of compute you throw at something. And this means that we're going to need to be able to algorithmically innovate, change the structure of our models, use kind of different properties than just throwing great big matrix multipliers at stuff. And that's kind of the other kind of trend that kind of has affected the design of the chip we've done. So we kind of looked at that. The other thing we looked at was what's happening with processors. So we want loads and loads of flops, we want loads and loads of performance in our chips. If you look at what happened with chips, is they're not getting any faster, right? So each one of this chart here is again time, and then this is a log grid scale again, and you can see that for a long time, a combination of two Moore's law, which is kind of empirical law about kind of the size, the reduction in the size of the components of a chip, transistors of a chip, and Demel scaling, which is about the amount of power you can get into the chip, meant that we had this kind of meteoric rise in the amount of compute you can get out from a particular piece of area of silicon. And then around kind of 10 years ago or so, it kind of stopped. So every processor from then on doesn't clock any faster, so it doesn't like process instructions anymore. So what we have to exploit is very high levels of power and, as I said before, better efficiency. So better capacity for algorithmic changes. It means you get more high level of functionality for the amount of compute you get through it. So we have to do something different than just like pumping out kind of physically faster and faster chips. We needed to address this idea that we wanted to have something that kind of addresses those compute and kind of does innovative things, algorithmically different things to what you can do with CPUs and GPUs currently. So we built this. This is the IPU, codename Colossus internally, which was the code name of the computer electric park that was built by Tom Clowes and Alan Turing during the Second World War, and first computer really. And it's also very big. It's probably about as big a chip as you can make on a single reticle, so a single kind of stencil if you like, as well. And it's been in production since the beginning of last year, and we've been working with various customers with it. It is a highly parallel big chip. It's got 125 teraflops of floating point precision, so it's a very highly spec'd compute chip. That's half precision floating point. And it's got a lot of on-chip memory and a lot of on-chip bandwidth. This allows you to focus on not just getting the high compute, you see that you need that, but also the innovative algorithmic changes by being able to swap around data in very different patterns in a very fast way. So that's what we made. And currently the way we're deploying that is we put two of those on a PCIe card, and those go into data center servers as well. So these aren't things that like you can put into your desktop computer. They're really designed for data center usage. Okay? And when we put these together, as you can see, they've got these connectors on the top to connect the cards together. I do for time, not well. And then the final thing I'll say about hardware before getting into the software is we now, as of a couple of weeks now, have announced the final kind of public products. They're still kind of early access in a way, but they're not behind closed doors really with customers that don't do so. Via Dell, you can now buy these cards and servers. They sell servers, and also we have them available as cloud compute on Microsoft Azure as well, starting this year. So we're getting to the point now where we've made these, we've got the software working for these, they're out there for people to use. I'm going to skip over this quite quickly. This is kind of like what the chip looks on the inside. It's lots and lots of processors, and unlike, say, a GPU, they're not all doing the same thing. It works on kind of independent task processing, and then they kind of explicitly program it by swapping data via BSP, if you're familiar with that. I don't think I need to go into that in this instance. So, that's what the chip is. The question is then, we've done something very different there. We've kind of tried to enable new things. That's the kind of long-term goal of the company. But we have to marry that with getting people to use it now. So how do we, which kind of is, and people have a way of programming now, which they're used to. Okay? So the obvious thing to do was to provide a software stack that allows, that kind of has high-level machine learning framework works at the top. So machine learning frameworks are great in that they provide a level of abstraction away from the hardware. They're also bad in that sense. But you kind of take away a bit of performance what you get in generality. And then you have to provide everything underneath that to kind of get you to the hardware. So what I'm going to talk about for the rest of the talk today is how do we open up high-level TensorFlow world, where you're just programming more TensorFlow, down to a brand new chip like this. What have we done in that journey? So this is our software stack. Let's say we start up here with TensorFlow, and there are obviously other frameworks around. Kind of support for PyTorch, support for Onyx, which is a standard interchange framework for neural networks. And then you have a lot of work to then get down to the actual hardware. And what we try to do is when people use our platform, we kind of want to open this up. Some people want to program just up here, some people want to program down here, some people want to program down here. It depends on kind of what you want to do in terms of pushing the envelope or looking at different aspects of performance. But what we definitely need is a good set of libraries to provide kind of the support for the basic operators you have, linear algebra basically. So let's go into that journey from the top of TensorFlow. So what do you do when you actually kind of get this out of the box? What does the user experience look like? And then I'll move down. So basically you have to install some drivers. You have to install our own version of TensorFlow. We've done a port of that works on our platform. I've done it in virtual env here. And you kind of can then just program Python as you would normally. So you'll take some TensorFlow code like this. This is doing some image classification inference. And as you can see, it's pretty standard kind of TensorFlow that builds around. There are some changes you may want to make, like this is true of all platforms on TensorFlow. There are default placements which we support as well, so if you don't make these changes, you default to the IPU, but you can specify kind of exactly kind of what device you want different places to run, and you can like give some configurations about how you want the hardware to work and so on. We have more kind of annotations on top of a standard TensorFlow compute graph, and that's all we have to do. So we put a lot of work into kind of trying to make this just a standard TensorFlow experience. This is an inference example, actually kind of a lot of our use cases are, but actually it's probably a mix between inference and training. And then when you use it, then you just run the Python program as normal. So I'm just going to kind of import the kind of model I've defined, instantiate it. At this point it does a graph compilation using the XLA. If people are familiar with XLA, if not, I'm going to go into it in a minute, which compiles the graph down to hardware, runs it, and then pushes the answer back up. So as we push kind of images into that, it does the classification just like you'd expect in TensorFlow. So for people who program TensorFlow, this should be kind of reasonably bread and butter stuff, right? Okay, so that's the end user experience. That's great. What happens in between? How do we go from something like this kind of high-level TensorFlow to something like this, where each tile has kind of machine instructions loaded onto it, which is going to run and do that work in TensorFlow. So I'm going to talk you kind of through that process. For a start, obviously, we kind of want a bit of an abstraction on this. So what we do in terms of that, we provide something called Poplar. Now, Poplar is a graph library. It's the framework where you program at the low-level device, where you can really control what the device is doing. If you're using GPUs, it sits at the same level as CUDA does for GPUs, but it's kind of very different in its approach. And you kind of see from the code, I'm not going to go through this, but you can see actually, because we have this kind of BSP-style multitasking processor, what we actually do is just specifying compute graphs and steps in the execution of the compute graph at the low level as well. And it's just much more fine-grained, so really big compute graphs for all these like thousands of processors that are running, but it's still a compute graph. And it builds up things like this. And that's our kind of graph programming framework. It's kind of very natural for this space. It's quite nice at that level, because even at the lowest level, you've got support for things like multi-dimensional data types and so multi-dimensional tensors and so on like that. Again, I can talk about Poplar all day, but I'm not going to. And then on top of Poplar, we build these libraries. So these are the things that use that low-level framework to do things like convolutions or matrix multipliers or nonlinearities or stuff on top of that. So that's kind of the level that you can actually program at that raises the abstraction up a bit. But we need to go from TensorFlow down to that level. So what happens there? Well, the first thing you get back in the TensorFlow is the core graph. So you would have seen this if you use TensorBoard. This is, just basically a graph that represents the kind of model you want to train. It also represents, say, the optimizer if you're training, and so on. And it's a very kind of high-level compute graph. This is a kind of textual representative. If you look inside the TensorFlow, you can actually output this, and this gives you kind of what the compute graph is. So this is the thing that TensorFlow takes and says, right now I'm going to execute, right? What happens then? Well, it identifies parts of those that compute graph, these clustering algorithm, which is inside TensorFlow, and says, I'm going to take parts of those and compile it down to different platforms. So for us, that's the IPU, it might be a CPU, whatever. Generally, graphs have multiple pieces of hardware, even if you're just doing on a single machine, because at least you have the CPU and the coprocessor. So we'll say, I'll take part of that and compile it down. And it will create, and this goes via something called the XLA, which is the internal TensorFlow compiler framework. So what happens there? Well, that produces something called the HLO graph, which is called the high-level optimizer graph. And basically what we do there is we take just pretty standard TensorFlow XLA and we've added some things to it. But this is all pretty much standard TensorFlow at that point. This HLO graph is a lot more low-level, so it's kind of broken it down a bit in a series of bearings. And then the next thing we do is we're going to take that HLO graph and we'll have, not just us, but any platform has kind of a platform-specific backend to produce it down to, in our case, this Poplar graph, which kind of gets split into lots and lots of little compute parts. Within those optimizations, we do a load of stuff. We do fusing. The hardware's got support for like kind of nonlinearities or logarithms or kind of standard operations, which is sometimes represented as multiple operations in the compute graph. There's things like graph outlining, kind of identifying common bits of the graph and like pulling them out. There's kind of analysis for data layout, how we're going to spread things over these processes and so on. So we're going to take patterns like this and then replace them with other more machine-specific patterns. That's the next step. So out of that, you get this, the HLO graph is less user-friendly, more machine-friendly at this point. It's much more low level, there's much more explicit information, all the sizes and the types are there and so on. So we've now got something that is slightly machine-specific, but it's still standard TensorFlow, that we're going to introduce to a totally machine-specific point. And the next thing that happens is each of those operators pretty much just translates into one of our libraries at the top of level to build a Poplar graph. That all gets compiled into one graph, gets put on the device, and then that's what you see. So I've only got a limited amount of time here, but I want to try and give an overview of kind of what goes on at the back end. Hopefully that's of interest to people. And that's basically it. When I say basically that's kind of like lots of people's work over several years, but that's basically what we do. But as I said, we want to really think about pushing the boundaries of what you can do with compute. So I also want to talk a bit about what we can do that's outside of the normal TensorFlow a bit, that kind of lets us do that. And there are lots of different areas we look at that, actually. But what I'm going to look at first is like large multi-chip systems and multi-chip models. So as well as like kind of our standard Poplar constructs and our standard TensorFlow compilation techniques, because models are getting bigger and bigger and bigger, this is not just on our platform, on every platform, you really need to look at how are you going to spread these compute graphs over lots and lots of chips. So we have, I'm not going to go through all these in detail, but we have lots of different methods of building up a toolbox of ways of splitting models over multiple chips. So we have things like sharding models, kind of putting different bits of the models on different chips, model replication, which is kind of more like standard data power scale up that people are used to, and pipelining, which is similar to sharding, but then trying to get kind of compute efficiency out of it as well. And we want to kind of get these new innovations at the low level, make them efficient, and expose them to all the frameworks we support. So TensorFlow and Poplar, which is our advanced runtime that goes behind some other frameworks, and Poplar and Seldon. So we really want to kind of push this out. One of those I will go into is pipeline execution. So if people aren't aware what pipeline execution is, what we're going to do is we're going to have each chip doing some part of the model in order. As one piece of data goes through kind of the pipeline, the next piece of data will start following it. So you kind of fill up all the compute, even though like different parts are doing different things on data at the time. So you can see that kind of in a picture here. So we have two chips, and we're going to split the model between those two chips. So as there's a forward and backwards path to a training run, it's going to do the forward pass to the first half of the model, then the forward pass to the second half, backwards pass to the second half, backwards pass to the first half. That's nature. You can see here you've got gaps where some IPUs are doing nothing. But by pushing more data through it, you can actually fill in those gaps with extra pieces of data and get like both chips do. So this is fine for 2. It becomes more interesting. There are more compute challenges as you do it for 4 or 8 or 16 or multiple chips in that way as well. So that's one of the aspects. It's actually not the only one we're looking at as well as chip. So we are trying to push in those directions. I just wanted to give a flavour of things. But we want to then expose this up to TensorFlow, so we have to extend the TensorFlow API a bit to say, like, kind of create your graph in a kind of normal way to kind of create a graph, but then kind of add constraints on how you're going to execute it to get efficiency. So again, it's kind of trying to get this idea that you still take this TensorFlow declarative way of defining stuff, but then kind of can annotate it with ways like you do replacements to actually push the efficiency up. And do new things. Yeah. Oh, okay. That's cool. So actually, I'm pretty good. So, so that's it really. What I tried to give here is just an overview of what we've done from the hardware and from the top to software, and kind of go from the top and work down as well. There's an awful lot to this, and we're kind of constantly pushing with this. What's really exciting now is that we've got this like position where we can start getting that out to more and more people and see what people can do with this. And what we're particularly interested in it is, as I said before, is the idea that we want to find people who are doing interesting new algorithmic things and try and push those boundaries. That's what kind of really interests us. And we're interested in like large deployments on standard stuff now as well, fine. But this is kind of like the long game for us. So that's all I've got to say today. I would like to say one more thing. This is a meetup, so I think it's obligatory to say that we're hiring. And we are. We're still growing. It's quite an exciting place where you're kind of like scaling up this company to become a sustainable business. It's a really exciting market. And if you're interested, either come and talk to me or there's people waiting at the back there about the various opportunities we've got. I started off actually in Graphcore, kind of actually looking at some of the software stuff, Poplar that we talked about. But actually now, as we go out to customers, we are looking for people working at that level and hardware level, but also the application level. And that's actually more what I do nowadays. It's actually the customer engineering division is more about kind of taking this and with customers doing interesting things with it, sort of machine learning engineers and people to support customers as well, kind of getting a view of kind of machine learning practice out there. So yeah, as I said, recently we're over the next kind of few months we'll be putting a lot more information on our website. It started with the announcement of the Azure Dell products. That means we're starting to slowly kind of open source more and more of our code. So you can see application code is now up on GitHub. We'll be adding more library code and so on as well, kind of as we go through the next few months as well. So So keep an eye on that, because it's kind of quite interesting from a kind of machine learning kind of application point of view as well. That's me. Thanks very much.
Does anyone have any questions for David? Yeah. If you can just give you your name and your company.
I'm Matthias, contractor from Softwares AI. I'm a machine learning engineer. I'm wondering, how do you envision people defining these models? Is it mostly through PyTorch and TensorFlow and PyTorch, or do you see people actually using your lower level primitives?
It really depends. It could be a combination, actually. There are kind of custom operators and optimizers you can do to combine the two. And actually, kind of we find that in certain areas, kind of people often, even if CPUs and GPUs don't just program TensorFlow, they'll program TensorFlow and a bit of like kind of low-level CPU code or CUDA code to kind of do certain parts of it. So it could be a combination as well. I think it depends on how exotic you're going to go. So kind of early on, I've always kind of tried to think that the ratio is probably roughly about 90% of people will be kind of TensorFlow, PyTorch, that kind of level, just kind of wanting to work. 10% of people will kind of want to go lower, and they're the ones that kind of have the requirement and need to add value in that way. And we really want to, if you looked at those percentages, you think, well, kind of, we just want to, if it's 90%, we just want to kind of fill their needs, really. But actually, those 10% are really important to us. We really want to open up that kind of level, because that's what pushes the innovation, pushes the value of our platform forward. So we kind of try to make it, try to really open up the stack and kind of make it work for everyone. That's probably the proportion I'd expect.
And if I may, one more.
Yeah.
And I was wondering, how fast is the recompilation of the graph? So for example, if I have a really dynamic model, this is like obviously working with pre-computed graphs.
Yeah. So it's not of the level where you do it kind of in flow with the model. You'd have to do it on a kind of a larger cadence. So it's more like kind of tens of seconds or a minute than kind of like milliseconds. So it is kind of, because one of the ways you get performance is by doing a lot of compiler optimizations at that level. There are other ways you can get kind of dynamic properties in a compiled graph, because we've got a lot of flexible control flow you can kind of push down to the device. So that happens in certain PyTorch models where if you've got recurrence or decision points, you just kind of push them down to the device and do them at runtime. If what you really are doing is recompiling all the time, it's not really suited to that unless it's at a larger cadence as well.
Hi, I'm Krisha Vilan from Martin AI. First, a small comment. The Cerebras chip has 1 trillion transistors, so it seems that it's maybe slightly bigger than concepts.
It is. It's not, well, the actual kind of, so it's a wafer scale chip. So the actual kind of, the reticle size is the same. So the amount you can actually stamp out on a chip, what they do is they stamp out 7 on a chip, and then like trace the communication paths in a way. So it kind of works more like, in terms of programming, I assume from what they've said. I don't want to comment on competitors too much. You can think of it as a cluster of several chips, but with fast interconnect that happens to be on the die rather than one big chip. I have doubts. I don't want to comment on competitors. I'll say that the chip looks lovely. I mean, it's a lovely thing that you can see. I wait for them to show how to program it.
I'm sorry, I will insist if you can comment a little bit on but to the extent you can. I'm just wondering about the data that you have 45 terabyte per second exchange of memory. And it sounds really a lot. And I'm just wondering, how did you achieve it if you compare it with GPUs, and is that electrical or optical connection? Or can you just elaborate maybe how do you compete with GPUs regarding memory?
Yeah, it's a very, very different memory structure. So it's a large-scale distributed memory as opposed to a kind of cached memory hierarchy, a kind of streaming memory hierarchy. So the memory losses are so different, it's kind of in some ways hard to compare. There's kind of secondary storage further away, and that's kind of similar. There's a lot more on-chip memory, and interconnect is an all-to-all, quite a bigger proportion of that chip. I don't know if I can go back. Oh, this is now your stuff, sorry. Sorry. Quite a lot of that chip is devoted to an all-to-all kind of exchange, kind of communication bus, where there's explicit message passing between the cores, and that's how we get the kind of increased memory bandwidth between them. So, I'm trying to say something other than this, they're different. But it is harder to explain the memory difference without kind of going into the execution model with. But yeah, it's basically a lot more on-chip memory and less off-chip memory, and no caches in between. So you directly kind of address what's on the chip.
So no caches between external memory and chip, or no?
Yeah, correct. No caches between external memory and on-chip. In fact, most stuff is kept on-chip because there's so much on-chip memory.
Hi, I'm Lacey. I'm from DNA Electronics. Can you tell something more about using this chip for like single devices, not in a like cluster computer context, but let's say for analyzing something on some bespoke instruments?
For kind of deployed embedded uses. Yeah, it's currently the short answer is the current generation of the whole hardware system platform we're not supporting that. That's just something we're delaying until later. So we decided, made a very explicit decision that what we want to look at initially is data center cloud compute. The architecture itself is designed to scale down very gracefully. So you can kind of make it smaller, make it lower power by just basically reducing the number of cores. Because the memory subsystem is kind of evenly distributed spread, you don't have an issue about what do we do about the memory bus. So it's definitely a thing for the future. But in terms of when you're a company our size, you really want to focus on one thing and get that right, prove out the technology, and then look into robotics uses, embedded uses, automotive uses, all these kind of things. They're all there for the future. This architecture is good for that in many different ways on a fundamental level. But right now, it's not really kind of what we're targeting.
Okay, thanks, David.